All right. So this is another important principle that we should know, right? In physiology, there's going to be what called like movements of molecules, right, across barriers. So molecules are always moving from one compartment to the other, which is super important. Things like absorption, oxygenation, etc. We're gonna need it. So first of all, we're gonna start with movement of um, non-electrolytes, right, and lipid-soluble compounds. What are the principles that will guide the movement of lipid-soluble molecules between compartments, right, or across barriers like plasma membrane and stuff like that? So here, the for lipid-soluble compounds and non-electrolytes, molecules are not charged. They are lipid-soluble, right? That is, they don't need a transporter. They can go through. So let's say this box, right, for instance, right, this box represents a plasma membrane. So we have height, we have the width, the thickness of the membrane and stuff like that. For a lipid soluble molecule to get from this side of this box to get to the other side, right? It can just go through, right? The membrane because it is lipid soluble, correct? Yep.
Yeah,
It does not
yeah.
need transport, it doesn't need help. Okay. But the question is how what will affect how fast? What will determine how fast the molecules will go through, how quickly you can start seeing the molecules on the other side of this box. So, and that's what the fixed law, right, of diffusion, right? This is what it's about. So this is a super important law, and you don't really need to know a lot here, but what we need to know, right, is a few things. First of all, the major things that will determine, right, how fast molecules will go, right, across this box, right. You can also think about it is what. Well, first of all, we need to create a force that will drive the molecules across, right, that will push them from this side to the other side, and that force is what concentration gradient. So if you have a lot of molecules here on this side, they're going to be bombarding each other, right? Like it's going to be overcrowded here. So guess what? Most of them is that by bombarding each other, it's going to create like a force, right? That will push some of the molecules across to the less crowded side, right? On the other side of this box, right? So the higher the concentration gradient, delta C, the faster, right? Molecules will move across because if they're overcrowded here, they're going to be bombarding each other, creates a force, right? That will push some of the molecules, right, quickly across to the less crowded surface on the contralateral side. Does this make sense? You got this?
Yeah,
Makes sense?
yeah.
How do you think the thickness of this box will affect diffusion rate? What do you think? How thick this barrier is, like the width we are dealing with, or the distance the molecules have to travel, what do you think about how that will affect how fast molecules end up on the other side?
In terms of the width,
Yeah, the width of the box or the thickness.
because of its thicker, because of its thick, it will get there slowly.
So if this box is thick, right, how long will
It
it take a molecule to go from this side to the other side?
take more time.
It's gonna take more time. So the thick, which makes sense, correct?
Yeah,
The thicker the barrier, if I have a very, very thick barrier like this box, imagine we increase the width, we have two of these box here forming this barrier. So they're gonna be the total distance of the length to get from this side to the other side is gonna be increased, double basically. It's gonna take more time for you to see molecules on the other side because they have more distance to travel through. Awesome. You get this?
yeah,
Right.
yeah.
And if the barrier is thin, let's decrease the width of the box. The box is very, very thin, like paper thin. The molecules will go through faster. You're gonna start seeing them on the other side earlier and faster because they only need to just travel a very, very short distance to get to the other side. Right. So imagine, let's take for example, right? Let's link this to pathology. What do you think happens to the diffusion barrier in the lungs when somebody has like pulmonary fibrosis, or they have fluid in the lungs, pulmonary edema, or they have pneumonia? What do you think will happen to the distance, the diffusion barrier, right? What happens to that thickness of diffusion barrier in those pathology conditions in the lungs? Does it become thicker or thinner?
Thicker.
It becomes thicker. It becomes thicker. Do you think it's going to be easy for oxygen to go from the lungs into the blood through that thick barrier?
No.
No. So you check the patient's oxygen in the blood, it's going to be low. You're going to say PO2 will be low because now it has to travel through a thicker barrier, longer distance. It's going to be very, very difficult. Yeah. So, and that will lead to what? Hypoxia. The patient will be gasping for air. They find it difficult to breathe properly. Right. That's the principle. So what do we normally do? How do we normally treat those people? So somebody comes, they have maybe pulmonary fibrosis, they have pneumonia, pulmonary edema, fluid in the lungs. You suspect there's oxygen in the blood goes down. They find it difficult to breathe. What do we normally give them? What do you give them in the hospital? You give them a face mask, right? A oxygen, right? Rebreather mask, correct? Yeah.
Yeah.
What are you trying to do with that? You're trying to push more oxygen, right, into the lungs, isn't it? That's what we're trying to
Yeah.
do. So by doing that, what are you trying to increase? You're trying to increase what? Your concentration gradient. Does that make sense? So I'm trying to
Yeah.
get more oxygen on this side of the barrier. If I get more oxygen on this side, guess what? More the oxygen will be bumping against each other. As they're bumping against each other, they're gonna create a force that will push more and more oxygen through that thick barrier into the blood, and that will help the patient breathe better. Right. That is what we're trying to. That's the principle. Awesome. Awesome. We got
Yeah.
this. Good. Right. So these are important. This is what? So concentration gradient is directly proportional, right, to the rate of diffusion, and the distance or the thickness of the barrier will be inversely proportional to the rate of diffusion. There's another thing that determines how fast a molecule, right, will go through, and it has to do with the property of the molecule itself, what we call the diffusion constant. What and the diffusion constant here is what? Is D, right? Is D. Diffusion constant here is talking about the property, right, of the molecule itself, the property of the molecule. So what happens is here it is determined. And the two properties we're looking at what is two things: the lipid solubility of the molecule. How well does the molecule love lipid? And secondly, we're looking at the weight of the molecule. How large is the molecule, or how small is the molecule, or how heavy is the molecule? And if you look at this very well, it also makes sense. So since the barrier we're dealing with here, right, is a lipid soluble barrier, is a lipid barrier.
Yeah.
Molecules that love lipid will go through faster than molecules that are water soluble. Does that make sense?
Yeah.
Right. So that is why, right? If you keep, let's say you keep every other factors constant, you keep the thickness of this barrier constant, you keep the thickness of the barrier constant is the same. Oxygen molecule will travel through a lipid soluble barrier or a lipid barrier slower than carbon dioxide because carbon dioxide is more lipid soluble than oxygen. Does this make sense? You get this?
Yeah.
Good.
Yeah.
Also if you look at the weight of the molecule is inversely proportional to how fast it's going to diffuse through the barrier, the weight, which makes sense. Molecules that are heavier, they're going to go through slower, right? They're going to travel slower. And same thing, you compare though of course this does not translate typically in real life because sometimes you can see a thin person that is not conditioned, right, and a big person that is very, very conditioned, so they can probably outpace each other. But let's say we have a lightweight person versus a big person. They are both athletes, they are both conditioned to run. Probably the lightweight person will probably run faster, right, if every other condition is constant, run faster than what a big person, because the big person will be dragged down, right, by their weight, right, law of nature and whatever. Same thing here. Molecules that are very, very large, they're gonna go slower, travel slower through this barrier compared to molecules that are what? Very, very small, right? Yeah. So the weight of the molecule is going to be inversely proportional, right, to the rate of diffusion, right, through the barrier too. So that's what we call. So these are the principles. So lipid solubility and concentration gradient and the area of the barrier, right? The bigger this barrier, right, the bigger the surface area, the faster the rate of diffusion, while the thickness and the molecular weight of the molecule are going to be inversely proportional, right, to the rate of what? Diffusion. Does this mean awesome? You got this? Great.
Yeah.
Right. So that is super right. So this principle is super important. These are the principles that guide how lipid soluble compounds or non-electrolyte, right? These are the principles that guide how fast they move, right, through a barrier, right? And they use simple diffusion. All right.